I'm not going to start the second part, just because I said so. So where we need to pick up then is right here. Maybe. Okay, phew. All right, so this is the slide after the assignment slide. We call it solving for equilibrium concentrations, because that's what we're doing. And we said, and you guys handed in homework, you said you can do that if you know, of course, the equilibrium, you know the initial concentrations of everything, and if you know one equilibrium concentration, you can kind of deduce the equilibrium concentrations of everything else. Well, in this case, you're not given the equilibrium concentration of anything, but you're given Kc instead. So here's the deal. It's going to involve algebra. So just bear with me. I'll do my best at teaching algebra, right? So we're basically going to have one equation, one unknown, and we're going to solve for x. We're going to set the changes. You know, in our ice diagram, our initial, our change, and our equilibrium, we're going to set the changes are going to all be in terms of some variable x. So basically, you know, if you have a coefficient of 2 in front of something and coefficients of 1 in front of something else, it's going to be, you know, 2x, 1x, 1x. So that's how that change part's going to go. So in our ice table, you know, like what you guys did for your homework, what you did was basically to take within a column, you took the first row and the second row, which was initial and change, you add them together and came up with that third row, the equilibrium concentrations. That's exactly what we're going to do here. But what we're going to see with our equilibrium concentrations is they're going to have an x in them. Then we're going to take those equilibrium concentrations that are our bottom row for our ice chart. We're going to stick them back in our Kc expression. And remember, we know the value of Kc. There is your one equation, and all you have are x's. One equation, one unknown. You solve for x. One equation, one unknown. And then once you have a value of x, and I'm going to show you, and you probably already know that with the quadratic, it gives you two solutions for x. One of those solutions is going to make sense, and the other isn't. So the one that makes sense, that quantity for x, basically you're going to substitute it back in there for your equilibrium concentrations, and you're going to go ahead and do a little subtraction and knock out your equilibrium concentrations. So I'll show you how that works. But these are the steps in a nutshell of how we're going to work these problems. And we'll pick on this equilibrium. We're going to do 2 examples. Okay, so yeah. Notice the Kc is given, okay, and then this information is given. Sometimes I'll like pull out the 2 moles of H2 and I'll put it where it is, okay? But now one of the things I'm going to emphasize this on your homework that's going to be due Friday. You cannot stick moles in your equilibrium constant expressions. You have to stick molarity, okay? So if it gives you moles, you better be looking for a volume. And we have a volume, 2 liters. So we're going to have to convert those moles. Or not convert, we're going to use moles and volume to get to molarity of H2, molarity of F2. So notice in this case, if you read it a few times, you're like, dude, there is no HF, and there isn't, okay? That's one of those. And notice that they give us the value for Kc. So the equilibrium constant expression for that equilibrium looks like this. So it's always products over reactants, and they're the molar concentrations raised to their stoichiometric coefficient. So let's go ahead and before I'm gonna, I think probably turn it over into an ice table here in a minute. But let's go ahead and fix those moles and you found your notebook. Let's go ahead and fix those initial moles of everything. So the little subscript 0 means initial. So this is going to be our first row, right, for everything. The molarity of H2 is 1.00. The molarity of F2, 2.00. And like I said, the molarity of HF, there is none. So let me go ahead and, I was going to do this ahead of time, but I kind of got sidetracked. All right, so I mentioned the ice chart. So here is your ice chart. And for some reason, I've seen it different ways. I think your textbook goes product or products and then reactants. I usually go reactants and then products. So I'm going to have 3 columns because I have you have 2 reactants and 1 product. So here are my reactants. H2, molar concentration of H2, molar concentration of F2, molar concentration of HF, initial, change, and at equilibrium. So we came up with some values to plug in here. The initial concentration of H2 is 1.00. Initial concentration of F2, 2.00. And there wasn't any HF. All right. And we don't have any equilibrium concentrations, but that's fine. And just to kind of remind us, we have our equilibrium constant expression, which is HF raised to the 2nd power divided by the molar concentration of H2 raised to the 1st power times the molar concentration of F2 raised to the 1st power. All right. Equals 115. All right. So here's the deal. And I should write the balanced chemical equilibrium, but you have that written down. Do you see where if we go ahead and make, first off, do you see where this change is going to be negative? Both of these changes are going to be negative. Why? Because we don't have any product, right? If we go ahead and make this a negative x, notice the stoichiometry between the H2 and the F2 is 1. It's a 1-to-1. So that means this will also be negative 1x. Okay. But do you see on the balanced equilibrium, if I want to say this in terms, first off, do you see where this is going to be plus? The change in my HF is going to be plus. Why? Because there isn't any. It's got to increase. That's where the plus comes from. Okay. And the coefficient in front of the HF is 2. So honestly, this is 2x. And then it kind of gets to what we've been doing before. We said basically for a column, for a given species, you take the initial, apply the change, and come up with the equilibrium concentrations. So down here, we got for H2, we have 1.00 minus x. For the F2, we have 2.00, which was initial, minus x. Okay, and for the HF, we have 0 plus 2x. Okay, now, to jump ahead to Unit 4, this is Unit 3. To jump ahead to Unit 4, some of you guys have already seen the syllabus. Unit 4, we're going to be talking about pHs. You know, hydrogen, acidic, basic, blah, blah, blah. I'm telling you, these ice charts are where it's at with regard to understanding pHs. The whole acidity, basicness of a solution is a tug of war. It's a chemical equilibrium. Okay, like it or not, that's the chemistry of pHs. So anyway, so this is an important thing in Unit 3 and Unit 4. All right, so now what you're going to see, and I think I might go back to my slides, is all we have to do is basically take this quantity, that's my molar concentration of HF, plug it in right there. Okay. Take this quantity, my H2, it goes right there. Okay, this quantity, my F2, goes right there. And I have slides to go ahead and show you that kind of substitution. And I'm going to write the word, I'm going to try to relay, there's 2 ways to work this, or two differences of completeness. I'm going to put stop here for exam. You would be done. Stop here for exam. Is that not a cool thing? But you aren't going to be done for your homework. because what you would end up with is all just one variable, the variable being x, one equation, and you can solve for x, and I'll show you how that works. Okay, so let me go back to the slides. Well, that was easy. Always something. All right. So like I said, on the ICE table for that C row for the change in, whatever's convenient, right? I think it's convenient to pick something that has a stoichiometric coefficient of 1 to make sure you keep your wits about you. Is it going to be a -1 or a +1x? Okay, but then they'll go ahead and let everything else kind of fall into place. All right. So this actually, notice the little e's here, the little subscript e's instead of little subscript zeros. Of course, that means at equilibrium. So that is our last row on our ICE tables. That's our equilibrium concentrations. These are the same amounts that we had on our ICE chart. But I like the ICE chart to help kind of organize things. And then here is a substitution into your equilibrium constant expression. Oh, no, I guess it's not. There's our ICE table. All right. Here are the substitutions back in. One of the things, the pitfalls, and probably if you do a lot of these, you won't fall into this, but it's really easy to lose your exponents. Very easy, okay? But do you remember what I told you? This is what, I'll write it again. Stop here for exam. So I guess if I was, I'm going to assign 5 problems here in a little bit. To me, as a minimum, you should work those 5 problems and at least get this far, okay? But that's not where it stops. So what we're going to do to finish it off is we're going to use the quadratic equation. We're going to come up with a real value for x, and then we're going to go back along that last row and substitute that value in of x and come up with the real equilibrium concentrations. Because now we don't have them, we just have them in terms of x. All right. Oh, yeah. So I'm going to show you how to get, I'll go back. This right here, this actually boils down to this. And I've not really ever done this for a class. How many years have I been doing this? I might have for years ago, but I'm going to go ahead and show you how you get from there to here. It looks like this, and it's called standard form. We call this standard form, or they call this standard form, because it is ready to use in your y is equal to mx plus b. So anyway, before I show you the quadratic, or remind you what the quadratic looks like, let me just show you what we ended up with. So this is the molar concentration of our HF squared times the molar concentration of our H2 times the molar concentration of our F2 in terms of x. That 115 is Kc. So to start out, I call it, and I don't know if somebody, when I was learning this, if somebody told me about this or if I just came up with it, I call it cross multiply or flatten out. So you see how I put the 115 over 1? That's just what I do. Because then clearly, if I show it as a ratio, I can go ahead and crisscross, cross multiply, flatten it out. So I end up on the left side with 2x quantity squared. Don't forget the squared. And actually this is, I can't tell you how much this is really going to help you if this works for you. Actually, you won't have to do this part, but you'll have to understand this part. And then I take the 115, and it's going to be multiplied by the quantity, the molar concentration, basically, of your H2 and your F2. Okay? I flattened it out. Now, you can do this a couple different ways. I went ahead and showed you how I distribute the squared through the quantity 2x. That makes it 4x squared. And then I went ahead and now I see also I took my 115 down because it's just a number. And what I focused on was the quantity 1 minus x times the quantity 2 minus x. I focused on that. Some of you guys already know how to do this. Okay. But what I did is I took the two numbers, the 1 and the 2, I multiplied them by each other because they're great because they're both numbers. 1 times 2 is 2. And then to get that middle term, I had to take the inside and the outside and add them together, okay? The outside is 1 times minus x, which gives you minus 1x. The inside is negative x times 2, which gives you a negative 2x. Negative 1x plus negative 2x gives you negative 3x. Now at this point, if you're dropping the decimals, that's totally cool, okay? Because I am here in a minute. But that's where that middle term came from. The last term comes from the multiplying the two outs things. So I have a negative x times a negative x, which gives me a positive x squared. That's where that last term came from. All right. So then my next step is to go ahead and take this 115 through. Okay, so 115 times 2 is 230. 115 times 3 is 345. Don't forget that's 345x. Like I said, I think in a minute I'm going to drop those decimals. 345x. And I will go ahead and post this up there too. And then the last one is just my x squared term. It's a positive x squared, so 115 times a positive x squared is a positive 115x squared. Phew! Now I'm ready to combine terms, and I'm going to go ahead and start to get it into the x squared, x, and my term without an x is equal to 0. That's standard form. Okay, so that's why I kind of moved it this way. So I can, subtract 4x squared from both sides, and that gives me 115 minus 115x squared minus 4x squared is 111x squared. That's where that term came from. There's nothing to combine with the 345x. Okay, and I bring down the 230x, and by subtracting 4x squared from both sides, I get that it's equal to 0. Okay, so the quadratic requires this, the x squared term, the x term, and the term without anything. So the number in front of the x squared is a, the number in front of the x is b, and the number without an x value is c. So those a, b's, and c's are things that you plug in. All right. I do not like the quadratic equation. Yeah, thanks. Good. Not even that teacher. So I said that. Notice I said that you get two solutions, and the reason, as you probably already know, you get two solutions is because this right here. You basically have to take it as if that's a positive square root, and then you take it as if it's a negative square root. So if you do that, and those are your A, B, and C, okay, it looks like this. All right. So on the next slide, I'm going to show you the two roots, but also I was playing around, and maybe you guys already know this. You can find anything on the internet. Remember, I will never ask you on a test to come up with the solutions for X. For two reasons. One is it's a pain in the butt. But the other one is people, well, I was going to say it's unfair with calculators. Some calculators automatically have it. And you guys can't use a programmable calculator. But there's this program out here. Check this out. You might use this for your homework. I posted it on Twitter feed just this afternoon. This is just one of many programs. But basically, it's a program out there where you plug in the 111, the negative 345, and the 230, and it spits you back to two solutions. And remember, for your homework, in order to get full credit, you're going to have to do that. There's like iPad, there's apps that do that too, but I thought this is more universal. Come on. Slow. I could have just pulled this up. Yes, it's right there.
Is it Rathway?
No, but that's probably a good one. And it's not Wolfram Alpha, because I bet they've got one too. It was that one you just saw. Come back. Here it is. I don't know, it's math.com/students-calculator/source/quadratic, okay? But my point here is, you know, if for this one, we put in 111 for A, and for the value of B, it was negative 345. I tried this in my office. And for the value of C, it was positive 230. And you hit solve. Okay, and I don't know if you guys have, if your slides are complete or not, but if you see these little two solutions here, 2.14 or whatever, 2.1399, wait, you know what I mean, 2.14, and 0.97. Those are the two possible solutions. Isn't that cool? And you can use that for your homework. I would use it for my homework. So back to the lecture notes. Okay, so 3 sig figs, rounding those to 3 sig figs. You get possibilities of x being 2.14 or x being 0.968. And here's the deal. Let's see if I can pull this up. This one. Here's our ice table, and if you've been working it this way, this would be your ice table too. Do you see what's wrong with that 2.14? You're like, if the change in concentration is 2.14 moles per liter, and it only had 1 to start with, then it's going to end up with negative molar concentration, right? So that one's out. It's that 0.9, whatever I said, 0.968. That one wins out. And that will be the way it always is. So here in a minute to finish up, and what you do for your homework is we're going to have to take that 0.968 and we're going to put it there to find the real equilibrium concentrations. 0.968, 0.968. So that's how that looks. Okay? So that's taking it all the way. And you should do that for your homework. Especially with that program. Come on. Okay? Very good. So, like I said, that last, to kind of finish things up, it would look like this. So that last row, and I'm not going to pull mine up, but that last row for the E equilibrium concentrations of everything, you could go from left to right. The molar concentration of H2 would be knocked down from 1.00 to 0.03. Now, when I go to rounding, I have a hard time rounding with these, so... But actually, I can see on my slide here, I'm rounding correctly since we're subtracting. I have to round according to decimals, so that's why that looks like that. This is to say that I probably give you a little more flexibility than some rounding issues. For the F2, we went from a molarity of 2 minus 0.968 to a molarity of 1.03. And of course, we had no HF to start with. Its change and its final concentration is 2x, 2 times that 0.968. 1.936. Now the reason this one is given 4 sig figs, even though there's 3 sig figs here, is that 2 is an exact number. There's no uncertainty. So it's like basically adding this to itself, which gives me 3 decimals. All right, let's do another one. Okay, you know this one's got to be harder, right? I don't think it's too hard. Can't remember what's different about it. But right off the bat, grams. You can't put grams. You cannot work with G's in your equilibrium constant expressions. So here in a minute, I'm going to basically, and we're given the volume, we're going to have to use the molar masses of these species to get from grams to moles, and then divide that by the volume to get molarity. So in this one, notice that notice that it says what direction are you going to have to go in order to get to equilibrium. Yeah, that's right, we have a little bit of everything. This actually, for your homework that's going to be due Friday, there's 2 problems just like this.
Does it matter if it's in Celsius?
Nope. No. The temperature up there just means that the Kc is good for that temperature. So we aren't going to use temperature, but it sets the stage for what the value of Kc is. So bottom line, here we go. Next to the first question, I'm going to write what my hint is for working these problems. You need to, let's see, I'll say calculate reaction quotient. If I put QC, calculate QC, that's your reaction quotient. Compare with Kc to get direction. In what direction must this reaction occur? That's how you figure that out. Calculate QC, compare with Kc. And I'm going to show you maybe why that's important, because when it comes to your changes, in order to know if it's a negative or a positive change, which direction it's going. Then once you get that figured out, you're back to just your ice table and kind of doing what we did before. So this next page is going to kind of do, just kind of showing you the strategy. We must determine in which direction the reaction will go. How? You calculate QC. Remember, your QC, your reaction quotients, are a snapshot. You get the snapshot based upon those grams, and then you compare to Kc. That's it. And once you get direction, you know if you need to make more products, those will be plus changes in the product part. If you need to make more reactants, those will be plus. It's easier to show you. Okay, so the equilibrium constant expression and the reaction quotient expression are totally the same thing. Equilibrium constant expression and the reaction quotient, same thing. Equilibrium constant expression at equilibrium, so that's that last row, right? Reaction quotient is that first row, initial, which may or may not be at equilibrium. It's kind of helpful that we have stoichiometry of 1 to 1 to 1 here. So we're in good shape. That should be easy. Remember that 0.190, that was given in the problem. That's your Kc, that was given. But I also told you, don't be caught off guard. Sometimes on my final, I'll put a question like this. Don't be caught off guard by something that doesn't have, that's a solid or a liquid. Okay, because remember, solids or liquids don't appear in the overall. Wait. Yeah, solid or liquids don't appear. All right. So I'll put all of these up here. This is like, I finally figured out why I get kind of itchy, kind of impatient. Like, this is Gen Chem 1 stuff. So in General Chemistry 1, we talked about how you could have a gas like that that's bouncing around in a given volume, be given the grams of the gas, and how do you get to the molarity of the gas. So the numerator of the first term in each one of those cases is the mass of that species. The second term is the molar mass of that species, the flipped version. And of course, underneath the mass is the volume. So this is how to get to the molarity of each of these gases. But I like this, because this is what I would try to do on my answer keys more. You see those little zeros? Okay, to be distinguished from little e's. Those zeros are initial. Okay, these aren't at equilibrium. These are just initial. They may or may not be at equilibrium. And those work great in your QCs, your reaction quotients. And that's where we're going next. So we're going to take those molarities, and if we substitute it back into your reaction quotient expression, we have of course, the molarity of the CO is that 0.795. The molarity of the BR2 is that 0.295. And the molarity of the COBr2 is that 0.454. So this is our snapshot. And we talked about this, gosh, was it? I don't know, maybe it was Monday, but it might have been Friday. So this is where we need to compare that snapshot with the real KC. And the real KC was that 0.190. So, of course, the QC 0.517 is greater than the KC 0.190. So that means if it's too big, what's in the top needs to get less. And what's in the top are the products. So actually this is a case where it needs to go from products back to reactants. So let's go ahead now and go ahead and knock out our ice chart. So basically your products is going to have a negative change, okay? Your reactants are going to have a positive change. How did you know that? This step alone. So here's what your ice table looks like. Maybe. Oops. All right. So kind of across the top, we'll go molar concentration of the COBr2 will be our first column. COBr2. Next column, the molar concentration of your CO. The next column, the molar concentration of your Br2. And again, we're going to be talking about initial, the change, and then apply the change to the initial, and you get equilibrium concentrations. Okay, so we know the initial of the COBr2 was that 0.454 molar. The CO was 0.795 molar, and the Br2 was 0.295 molar. Okay. And somewhere, just to kind of make us all feel warm and fuzzy inside, we could write the equilibrium constant expression. Kc is equal to, and we're given Kc, the molar concentration of CO times the molar concentration of Br2 divided by the molar concentration of COBr2 is equal to that 0.190. All right. So the whole bit we did about seeing that Kc was larger than Qc, okay, means that, like I said, we need to go from products back to reactants. So that's why I'm going to put a negative there, a negative here, and a plus here. That whole comparing QC to KC, that's how we got that. And the stoichiometry is 1 to 1 to 1, so guess what? Does that make sense? So now all I need to do is I can write those equilibrium concentrations. So for the COBr2, it's 0.454 plus X. For the CO is 0.795 minus X. For the Br2, it's 0.295 minus X. Then all we got to do is to plug in these numbers. This quantity goes down there. These two quantities go here. And you would be done on the test. So here's what that looks like. Okay, so this slide is just knocking out those equilibrium concentrations. Your reactant is going to increase by X, so 0.454 plus X. your products are going to both decrease by x. So 0.795 minus x, 0.295 minus x. There's your ice table. And here's what it looks like substituted in. So like I said, just make sure we're all on the same page here. You could stop here for exam. But especially that kind of flattening out part that I showed you is probably something you want to be able to do. So if you flattened it out, getting it in the standard form, this is what it looks like. So your A is 1, your B is negative 1.280, and your C is 0.148. Okay, so I'm not going to do it, but you could find any of your favorite program to solve your quadratic equation, put it in, and you come up with two possible values. And here's your two possible values. Okay. So 1.15 or 0.129. Just to remind you what that ice table would look like. Do you see where the 1.59 does not make sense? 1.15, I guess it was. Right here, you can't subtract more than you start with, okay? But the other root is fine. So then to finish up, what we're going to do is to take that x and plug it in the last row and come up with the real equilibrium concentrations for those three species. Okay, so at equilibrium, if you're doing this on your ice chart, of course, this would be the reactant. So the molar concentration of your COBr2 is 0.583. The molar concentration of your CO is 0.666. Ooh. The molar concentration of your Br2 is 0.166. And that's it. Oh my gosh, I forgot to say like the coolest thing. So, do you guys see where we could actually check this? Okay, your equilibrium constant expression looks like this. Okay, it's Kc, okay, and you know the value of Kc because you had to use it in your problem. Okay, but Kc is the molar concentration of your product, 0.583. raised to a stoichiometric coefficient, which is 1, times the molar concentration of your reactants. That should be equal to, dun dun dun, that 0.190. Don't you love problems that you can check? I do. They're good and bad. Did it come out right? Close? Very good. So that's a thought, right? It's kind of fun. Okay, so let's take a look. And I've already kind of given you a hint that these two problems, I'll go ahead and tell you, you need to calculate a QC first and compare it to your KC. These other problems are just ice charts. Initial change, apply the change to get the equilibrium. So I don't think I have a lot of hints, but I'll show you what I got. Up here. Whoops. All right, so the first one, I know it's a little fuzzy because I use a different program to get it. But darn it, they give you moles. Why don't they give you molarity? But they give you moles and volume, so you're going to have to make sure that you get 2 molarity. You have 2 reactants in 1 product. You don't have to figure out which way it's going, because if you read it a few times, and trust me, it takes me a few times to read it sometimes, you find out there is no product. Okay, so it's going to have to go in what we call the forward direction. So then for that reason, we know it's a minus x plus 2x, because there's stoichiometric coefficient of 2 in front of the HI. So that's our change, okay? We can go ahead and come up with these green circles. Those are equilibrium concentrations in terms of x. Okay, remember, we'll have real numbers there. Okay, then you take these and substitute them back into your equilibrium constant expression. This in purple just reminds you that the 50.2 was given. That's your Kc. So basically, you'll have, something minus x quantity squared, divided by something minus x times 2x here is equal to that number. Let's see, what did I say? Oh, then what I wrote here, that was my plug. Then I wrote here, and I said green, would be done on exam. This, when you turn it in terms of x, you would be done on the exam. Okay, and I said homework solve for x. So you're going to have to me, flatten it out and get it in standard form. The whole x squared, x, and no term. So, but if that just makes you queasy, at least get that far, okay? Set up your ice tables. They're fun. Again, you must calculate molarities. In this case, you're given moles and volume again. The molarity of everything. Okay, so notice in this case you don't have any of the reactant. The SbCl5 is 0. The coefficients are all 1, which is kind of nice. So you have a plus x, a minus x, and a minus x. Okay. Go ahead and get your equilibrium concentrations in terms of x, and then same as previous problem. And this one, darn it, you're not even given moles, you're given grams. You're going to have to use the molar masses of those things. It's good practice. Must calculate molarities. Okay, and then you'll have 4 columns, right? They're all gases, so they all appear. You can get the equilibrium concentrations. Notice that you don't have any CO2. And I thought about this a while. You really don't have to figure out which direction it's going to go because you don't have any CO2. Okay, and CO2 is a product, so it's going to have to go this way. So that makes these plus x's, stoichiometric coefficients of 1 across the board, and these are minus x's. Okay, get your equilibrium concentrations in terms of x's, then same as previous problem. Then the last two, again, you're given in terms of moles and volume, and you have to calculate, get the molarities. But this is one of those where if you read it a few times, notice that you have a little bit of everything. If you ever have a little bit of everything, you don't know which way it's going to go to reach equilibrium. You might be at equilibrium. Your QC might be equal to your KC. Okay, so you're going to have to come up with those initial concentrations, plug them into your reaction quotient expression, knock out a QC, compare that to the KC that was given of 2.00. Okay? And only then can you know if you're supposed to add or subtract the change. Okay? Coefficients, be careful. We do have a coefficient of 2 in front of the COF2, coefficients of 1 in front of the CO2 and the F4. So that's why I kind of put plus or minus, because I didn't know. You're gonna have to find out. So this is going to be either plus or minus 2x, and then this will be either minus or plus x or minus or plus x. Okay. And then it's the same as the previous problems. Okay. Good stuff. And is that it? I think that's it. Oh, okay. There's one. Oh, that's it. No. Very similar to problem number 28. Smiley face. It really is. You're going to have to do the whole, come up with a snapshot QC and compare it to KC to know whether you're adding or subtracting your changes.
Yeah, that's what I was thinking.
Oh, 38. Thank you. You guys are good. My other class, there was a mistake, and I'm like, oh, wow, you're right. Only one thing? Okay. So there is a study session today, and I know a few intro students are going to go.